And then the other theme is just trying to connect how just basic visual observing of the night sky can help us to connect and understand the physics of what's going on. I'm not going to be going into any super deep technical details here, but just to kind of tie together the connection between what we see in the sky and what's actually happening. Because our perspective of how we view things from Earth can often make things look kind of strange and weird. And sometimes you have to almost kind of leave Earth to try to understand how things are happening. And the history of people trying to understand the stars and the sky is them understanding how things were moving around and building models and trying to understand how it all worked. Away we go. So yeah, I'm going to be talking about Saturn and Jupiter in the sky in December of this year. And away we go. So first off, I want to just do a little pitch here. I'm going to be showing a lot of screenshots from a software program called Stellarium. Stellarium is a really, really cool software to allow you to simulate and predict what the sky is going to look like. And the great thing about Stellarium is, first, it's completely free. And as you can see, you can download it for pretty much any operating system, Linux, Mac, Windows, or they even have a version where you can run it directly in a web browser.
Jeff, next time you come, me and you are going to have to use it.
Yep, absolutely. So if you either just Google search for Stellarium or go to stellarium.org, you can download Stellarium. And what it lets you do is it lets you basically pretend like you are in any location on Earth, and you can set it to any date and time, anytime in the past, present, and future, and it will then simulate for you what the night sky is going to look like. So it's a really, really cool tool to help you understand how the stars move around and to see what everything's going to look like. So you'll see throughout this presentation a lot of screenshots from this software, Stellarium. Pretty powerful, and again, the fact that it's free and available on any operating system is really, really neat. And so using Stellarium, take a peek at a view in the southwest direction at a very particular date. If you notice, I'm simulating here December 21st of this year at about 6 o'clock at night. And there's something really curious going on here. You can notice there's some labels like the moon and some of these satellites, but the labels here are a little bit mushed up. So if we zoom in to see what actually is happening there, what we see is that's actually Jupiter and Saturn that are really, really close together on that date. Jupiter and Saturn, some of the really most interesting and easy to look at objects with a telescope or even a pair of binoculars. So before I jump into this any deeper, I want to get a little bit of a background about how we measure the distance between objects. So objects are really, really huge and they're very far apart. But for example, we don't often talk about the size of the moon in like feet or miles. We typically talk about it in an angular size. So what angle the object occupies, or the angle between two objects. And obviously the size of the object combined with its distance will lead to the angle. But in astronomy, when we talk about objects in the sky and their either size or their distance apart, we talk about that in terms of angles. And to get a little bit of a calibration there, we have some little tricks that we can use to measure the angles. By holding your arm out at arm's length, you can actually measure the angle using your various tricks with your hand. So for example, if you hold out your pinky finger, again at arm's length, that pinky will occupy about 1 degree of your view. If you put up 3 fingers, that's roughly 5 degrees. The width of a closed fist is about 10 degrees. And if you do the, pinky and pointer finger, those spread at about 15 degrees. And then finally, if an outstretched thumb to an outstretched pinky is about 25 degrees, which happens to be about the size of the Big Dipper. So you can use some of these real simple tricks when you're out looking at the sky to measure how big things are or how far apart they are. So just to help kind of build a little bit of intuition of using angles to measure things in the sky. And so, for example, one of the most common objects that we looked at is the moon. And the moon seems huge at some times, but actually it's pretty small. The moon is actually half a degree across. So it's a half a degree in diameter. And from the previous slide, I mentioned your outstretched pinky is about 1 degree. So you can actually cover up the moon twice by simply reaching out your pinky finger. Okay, so the moon is about a half a degree in diameter. So again, another little fact to keep things in perspective. And so now if we take a closer look at that image and looking at Jupiter and Saturn, and again, remembering that in the relative size of things, the moon is about a half a degree across, Jupiter appears much, much smaller. Again, Jupiter is much bigger than the moon, but the fact that it's a lot further away, it appears smaller. So the diameter of Jupiter appears to be about 1/100th of a degree. So a lot smaller than the moon. And Saturn is about half the size of Jupiter. So 5/1000ths of a degree across. So pretty small, which is why when we look at them with just our eyes, they almost appear like stars. They just seem like dots. But if you were to look at them through binoculars or a telescope, you would actually see the disks and then the planet. But the interesting thing this night, on December 21st of this year, the objects themselves, Saturn and Jupiter, are only going to be 1/10th of a degree apart. That's really, really close and really exciting for some reasons that I'll get into a little bit later. And again, if you keep in mind the perspective that the moon is half a degree apart, and these are 1/10th of a degree apart, you could fit this distance 5 times over again within the moon. So the idea is these two objects, Saturn and Jupiter, are going to be extremely close together on December 21st. And a little chart here is showing what the separation of Jupiter and Saturn is going to be, starting about now and going all the way through towards that 3rd week in December. So right now it's November 23rd, so they're about 3 degrees apart. So 6 times the diameter of the moon. And so if you were to go outside and look, you would see that they're pretty close together, but still pretty far apart. And as the days progress, as we get closer and closer to December 21st, you see that they get closer and closer together until December 1st when they reach their closest, which is 1/10th of a degree. And then at that point, they start to drift further and further apart from each other. So that's really, really exciting and really rare, which I'll be demonstrating in some slides a little bit later on. So just as a refresher, this is the view of Saturn and Jupiter on December 21st. And again, just to build a little bit more intuition and to put it in perspective, here is the moon behind those two objects. Now, a big thing to note, the moon will not be behind Jupiter and Saturn. In fact, if we could see Saturn or Jupiter in front of the moon, that would be really, really bad news because they are actually further away than the moon. But I show this image just to get a little perspective. If they were lined up like this, here's the moon and here's Saturn and Jupiter. So if you think about how small the moon looks in the sky, you can get an appreciation for how close together these two objects will be. So really, really cool. The neat thing is, I don't know if anyone in this chat has had a chance to see either Jupiter or Saturn through a telescope. They're both fantastic. Through even a fairly modest telescope, you can clearly see the rings of Saturn, and you can see some details on Jupiter, as well as Jupiter's moons. But the really neat thing, and the thing that's quite rare, is to see them both at the same time through a telescope. And what I'm simulating here is this is the view through a telescope that I'm showing over here, a fairly basic, not terribly expensive, 6-inch diameter telescope that you can buy for about $400 with an eyepiece that actually comes with it. And this is what the view will look like, again, on December 21st. So through the telescope, you will be able to see Saturn and Jupiter at the same time, which is really neat. And again, as you'll see in a couple of slides, something I've looked at Jupiter and Saturn hundreds of times, but have never been able to see them at the same time through the telescope. This $400 telescope comes with another eyepiece, which actually allows you to zoom in or magnify the view a little bit. And what you can see if you flip back between these two slides, by magnifying it, Jupiter and Saturn actually get further apart. But what that does is that brings up more detail. So again, with a really basic, easily, affordable $400 telescope, you will be able to see the details of Saturn and Jupiter and at the same time. So that's really, really exciting and something that I'm looking forward to. But there's a little bit of a catch, and something that we have to be mindful of and aware of. So what I'm simulating is using that software Stellarium, I'm simulating the progression of the night starting at around 5 p.m. And as you can see, around 5 p.m. in the southwest, you start to see the sun beginning to set. If you can make out these little pink crosshair, that's where Saturn and Jupiter are. But because of the fact that the sun is still above the horizon, they're difficult to see.
Jeff?
Yes.
I had a question.
Go for it.
The question is, as they get closer together, will they also be getting closer to the Earth, or are they still the same distance away?
I would say the simple answer is the same distance away. Maybe subtly different in terms of maybe a subtle bit closer or further, but effectively the easiest answer is they will be the same distance from Earth. But they are appearing to us to be getting closer and closer together for reasons that I'll explain a little bit later in this talk.
Okay, thank you.
Absolutely. Does that answer the question? Yep. So they won't appear to be getting bigger or smaller by drifting closer or further to the Earth, but they will appear to get closer to each other. Great question. Thank you for that. So again, we start at 5 o'clock where the sun is just not quite set yet. We advance about an hour later to 6 p.m. and you can see the sun is just starting to get below the horizon. And according to this simulation, Jupiter and Saturn, which again are really close together, so only Jupiter is showing up in its label, is just starting to appear. Then I go forward just another half an hour to 6:30, at which point the sun is fairly set. The sky is starting to get pretty dark at that point, and Jupiter and Saturn are now pretty evident in the sky. And it's 6:30. But then I go just another half hour later, and you notice that Jupiter and Saturn themselves are starting to set. So there's just this really narrow window between the time that you can see Jupiter and Saturn when the sun is set and it's dark enough to see them easily, and the time that they set themselves. So there's only a really narrow window on December 21st when you'll really be able to catch them. So that's something, again, to keep your mind on, and I'll be talking about that a little bit later on as well. Again, by 7 o'clock, pretty much at the horizon. And so another little chart here, what I'm showing is the time that Jupiter and Saturn are setting as the days go on. So as you notice, as the days go on, Jupiter and Saturn are setting earlier and earlier and earlier, which again is not good news because the earlier in the evening they set, the less time we have to observe them. So for example, right now, they're setting at around 7:30 at night. And the fact that it's dark at 5 or 5:30 means there's plenty of time to see them. As we get closer and closer to the time that they're at their closest, you also see what I'm showing here in the red is this is something called astronomical twilight, when the sky starts to get really, really dark. So the idea is there's only a little tiny window between astronomical twilight and when the object's set. And that gap narrows as we get further and further into December. So that's something a little bit working against us, but again, it's not a total disaster.
Jeff?
Yes.
I believe, never mind.
Okay.
Answered.
Perfect. The other thing to think about is the Jupiter and Saturn are setting at about 7 degrees per hour. So the other thing to keep in mind, some of these images that I was showing don't have any trees, don't have any buildings and other things. So it's possible that even though in this image, Jupiter and Saturn are technically above the horizon, depending on where you're trying to observe them from, they may be behind a tree or behind your neighbor's house or behind some tall buildings. So again, another little thing not quite working in our favor. But again, there'll be some good news in the end, so just hang in there with me. So I bring in now that chart also that I shared in the beginning, which is what the separation is. And the key here is, as time goes on, the separation gets closer and closer and closer. And I would argue that as Jupiter and Saturn get closer and closer, it's more interesting. But also as they're getting closer and closer, we're battling the fact that they're setting earlier and earlier in the evening. So there's that balance to be played. Earlier in the month, they're more separated, but you can observe them longer because they set later at night. But as time goes on, they get closer and closer, but you have a narrower window to observe them. So there's that balancing game in there. And my argument, what I'm suggesting, is to observe them continuously throughout this time. And I'll talk about that again in a few slides here. But before we dig into that any deeper, I want to take a moment and say, why is this happening? Why are Saturn and Jupiter appearing to us to get so close together like that? So I'm going to run a little animation here. And as I said at the beginning of the slide, sometimes to understand these things, you have to kind of take the view off of the Earth. And so if you notice, what we're looking at is, this isn't an exact 2-scale drawing, but it's an animation if we're sort of above the solar system looking down. So we see the sun in the center, and then we see the Earth, Jupiter, and Saturn. Note there's other planets, but they've been omitted from this in order to keep it clear. And what you'll see when I start the animation is all of these will then be orbiting in a counterclockwise way around the sun. But the planets that are closer to the sun will be orbiting faster than the ones that are further away from the sun. And so in the next slide, when I start the animation up, I'll do a little bit of a voiceover, and you'll start to see why this Saturn and Jupiter proximity happens. And just to key your brains into it right now, imagine if you were sitting on Earth looking away from the sun, because typically when we're observing the night sky, the sun is behind us. So if you were looking out this way, if you could imagine, your eye would see Jupiter and Saturn very close to each other. So with that, I'm going to start the animation here in just a few seconds. And you'll see the year over here. So you notice every time the Earth goes around the sun is 1 year. And Jupiter is going around the sun a little bit slower than the Earth. And even slower still is Saturn, which is going around very slowly. And we're at about 16, 17 years. And you notice at the 20-year mark, they line up again. And then Jupiter moving faster than Saturn. It's almost like a race. Saturn and Jupiter is pulling ahead and moving faster, and Saturn's leading behind. But because Jupiter is moving faster than Saturn, you can notice it's about to catch up. And at year 40, they line up again. And then Jupiter pulls ahead and is moving faster and faster. And as it pulls ahead, Jupiter and Saturn would be appearing to us to be separating in the sky. And we're at about 50 years now. And you can see Jupiter is once again catching up to Saturn until they meet again after 60 years. And the interesting thing after 60 years is they're once again lined up and in the same part of the sky. So we have this 60-year cycle, which again, I'll be talking about in another slide. So I've been using the word Jupiter and Saturn getting close together, but the real term is this is called the Great Conjunction. A conjunction is simply the appearance of two objects being close to each other in the sky, and they reserve the word the Great Conjunction for the conjunction of Jupiter and Saturn. And a little bit of math here. I promise this is the only math, and it's really not all that heavy. But Jupiter's orbital period is about 12 years, which means it takes 12 Earth years. And remember, a year on Earth is how long it takes the Earth to go around the sun once. It takes Jupiter 12 years to go around the sun once. Saturn, being further away, takes about 30 years to go around the sun once. Okay, so Jupiter takes about 12 years to go around the sun. Saturn takes about 30 years to go around the sun, which is why in that previous animation, you saw that Jupiter was going around a lot faster and then would occasionally catch up with Saturn. So a little bit of math here. If you take these two and you plug them into this formula, what you find out is you have this conjunction once every 20 years, which, if you remember from that animation, lines up with exactly what we saw. In that animation, once every 20 years, you would see Saturn and Jupiter aligned together. So that 20 years is an important number to keep in mind. Because here is a table of some of the past and future great conjunctions. And first of all, if you look at the dates, you'll notice they happen every 20 years, starting from the 1800s, every 20 years, all the way up to now, 2020, and then a couple of them in the future. So there's a couple of these conjunctions that I would like to highlight here because they're certainly noteworthy. And we'll start with the one in the year 2020, so the most recent one from 20 years ago. So here's a simulation of the western sky, again, on May 31st of the year 2020. And you can see here is Jupiter and Saturn, again, in their conjunction mode, very, very close to each other. There's the moon down here. But there's one other interesting object in this view, and that's the sun. So wait a minute, if the sun's up here in the sky, why does it look so dark like this? Well, there's a trick in the Stellarium software where you can actually turn off the effects of the sunlight, which normally washes out all these other objects. So this is really a trick photo, for lack of better terms, in that this is not really what the sky looked like. And if you noticed over here, late May at 5:30 at night is still daytime. So the answer is this, and I'm going to show you another daytime conjunction, and we can see the impact of that.
I have a question for you, Jeff.
Go for it, Kim.
And you're probably going to answer it right now, but the question is, what exactly is a triple conjunction?
I will get to that. That's a fantastic question.
Okay.
So now we focus on, again, the conjunction of December 21st, 2020. The big thing I want to point out is, as is highlighted here in this table, this is the closest conjunction, meaning during the conjunction, Saturn and Jupiter will be the closest that they have been since 1623. So I'm not sure if anybody in this call saw the conjunction in 1623. I wasn't around at that point. But if you look backwards from the 1800s, you notice a lot of these, like the one 20 years ago, even though Saturn and Jupiter were close, they were still a degree apart. That's twice the diameter of the moon. Again, back here in 1980s, a degree apart. Okay, so this one is really, really special in the fact that Jupiter and Saturn will be extremely close together, a tenth of a degree apart. And as is highlighted again, this one's really cool because this is the closest that Jupiter and Saturn have been since 1623. That's really, really neat. Next, I'm going to highlight the next conjunction, which is going to be on November 5th, 20 years from now. So the year 2040. So again, I'm simulating the night sky. I'm simulating the sky on in the year 2040. And again, you can see Saturn and Jupiter here. Again, here's the moon. There's some other interesting objects, Venus, Mars, Mercury, all these guys all lined up, which is really neat. But once again, there's the sun. And if you look down here, this is simulated at 5:30 at night. So the sun is still above the horizon. But like I said, in the one from the year 2000, I did a little trick in the software, which was effectively to deactivate the effect of the sun. What I'll show you in the next slide is what the sky would actually look like at this date and time. And so this is what the conjunction actually looked like, or I'm sorry, will look like in the year 2040. So unfortunately, 20 years from now, we have another conjunction, but we're not going to be able to see it as well because it's going to happen during the daytime. The next conjunction, April the 10th of the year 2060. Again, so we're simulating April 10th, 2060. There's Saturn and Jupiter in the sky. Venus is up there. Some of the big stars, Sirius, Rigel, Betelgeuse, one of my favorite stars. I just love that name. great movie too. But the good news is what you see here is no sun. So this conjunction is actually going to be visible like the one this year. But I hate to be the constant bearer of bad news because, as some of you may have picked up on, we're talking about the year 2060. And I'll let everyone in this call do the quick age math and figure out how old they will be in the year 2060. And let everyone draw their conclusions from there. 40 years from now, we're all going to be about 40 years older than we are now. So the big point that I want to reinforce is the next conjunction 20 years from now will be during the daytime, so we will not be able to appreciate it as much. And then the next conjunction after that will be 40 years from now. So the fact that we have this one right now, not only is it the closest conjunction since the 1600s, but it's probably the last really, really good nighttime conjunction that most of us are going to have in our lifetime. So keep that in mind. And again, not all doom and gloom, but just to really reinforce how special the conjunction this year is and how this should be a motivation or inspiration for us to take advantage of it. And as promised, in 1981, I was 5 years old and had no clue that anything like this was going on. We had something called the triple conjunction. And so actually, let me back up a second. So that was a fantastic question before. What is a triple conjunction? So what I'm going to show in this slide is this is an animation where every frame is jumping in 5-day intervals. So you can see Jupiter and Saturn are getting closer and closer. So we have a conjunction now. And then as you see, as the days go on, they're getting further and further apart. And if we just let this animation roll, all of a sudden, Jupiter and Saturn have done something weird. They've stopped and they're now moving backwards. So they got closer together again. So we had a second conjunction. Now they're pulling further and further apart as they're drifting towards the left in the view from this slide here. And Jupiter and Saturn are getting further and further apart. Let me see what. Okay, so yeah, they're pulling further and further apart, and then they pause again, and you see they now start moving to the right, and they're also getting closer and closer together again. And again, not that I expected anyone to be counting in their heads, but keep in mind each jump or each frame here is 5 days. So what we had in this animation was we actually had 3 conjunctions occur within 6 months. That's why it's called the triple conjunction. As I mentioned, they typically only happen once every 20 years, except something really curious happened here, which is that we had 3 conjunctions within 6 months. So that kind of broke the rules, for lack of better terms. And so the question is, why did that happen? Well, a clue to that is also the curiosity that Jupiter and Saturn seem to be doing this weird thing where they're moving to the left, and then they move to the right, and then they're moving back to the left again, which is really odd. So I'm going to explain that here in the next couple of slides. So the triple conjunction is due to something called retrograde motion. Now, some people may have heard the word retrograde in different contexts. And the key is most planets appear to move westward against the pattern of the background stars. And in this animation on the right, you can see that typically, now this is looking at the retrograde of Mars. For the most of the animation, Mars is moving to the west, or in this case, what would be to the left. But occasionally, one will appear to move eastward, like you see right now, for a temporary amount of time. This is called retrograde motion. This retrograde motion is due to the relative alignment of the Earth and the object in retrograde. And so if you kind of take a minute and let this animation here absorb, the relative position of Earth and Mars against the background stars makes it appear to do this weird zigzag or retrograde motion. And actually, in the next slide, you guys are going to get a little bit of a break from my voice, and I'm going to be showing you a YouTube video that explains the retrograde motion in far better detail and much more clearly than I possibly could. I hope this works clearly. If anybody's having an issue with it being jumpy, please let me know. But this is about a 5-minute video, so I'll take a little bit of a pause here and let you
Jeff,
guys enjoy this video. Yes, Kim?
I'm sorry. I just wanted to let everyone know, we did a sound check on this earlier, so it's a little difficult to hear. So, but if you turn your computers up, you should be able to hear it.
Yeah, thanks, Kim. Yeah, the audio from this video seems to be quieter than my voice, so you might want to make that volume adjustment when this plays. So thanks for that heads up, Kim. Let's see how this goes.
In the night sky, stars rise and set due to the rotation of Earth. However, the pattern of stars that is seen in the sky, how far apart a pair of stars are seen from each other, stays the same over timescales of thousands of years. However, planets move in the sky relative to the pattern of background stars. They change their position in the sky from night to night. The term planet originates from the Greek word for wanderer. This phenomenon can't really be seen on any given night, but if you note the location of a planet relative to the background stars, and note its location again several nights later, you will see that it has moved. This could be seen if you took a series of photos every night for a month with a chosen star highest in the sky and laid them over the top of each other. Planets typically move eastward, the direction of increasing right ascension, which we know today is due to their revolution around the Sun. Note that a planet still rises in the east and sets in the west on any given night due to the rotation of Earth. This video will focus on a variation of that motion known as retrograde motion. This apparent motion concerns the planet slowing in its eastward motion, stopping, moving westward for a while, and stopping again before continuing on its eastward journey. For superior planets, those that orbit the Sun further out than Earth, and the only planets that will be discussed in this video, this effectively creates a loop in the sky. 2,000 years ago, the Greek astronomer Ptolemy explained retrograde motion with a geocentric system of wheels within wheels, kind of like the kids' drawing game Spirograph. It was believed that Earth was at the center of everything and that a planet moved on a circular path called an epicycle, the center of which moved on a larger circle called the deferent. This allowed the existence of retrograde loops to be explained, although in a complicated way. We know today that this explanation was completely wrong. In the 1500s, Copernicus explained retrograde motion with a far more simple heliocentric theory that was largely correct. Retrograde motion was simply a perspective effect caused when Earth passes a slower moving outer planet that makes the planet appear to be moving backwards relative to the background stars. Thus, retrograde motion occurs over the time when the Sun, Earth, and planet are aligned and the planet is described as being at opposition, opposite the Sun in the sky. This is why retrograde motion is referred to as apparent retrograde motion by many. Nothing is changing in the planet's motion, and retrograde motion occurs as a natural perspective effect. Let's look at a demonstration for teaching retrograde motion. It consists of the Sun at the center, in red, Earth and a superior planet in a circular orbit around it. Here, a white rod connects Earth and a superior planet similar to Mars and represents the perspective, pointing to the location where Mars would be seen in the sky from Earth. East is counterclockwise around this circle. A system of circular gears controls the positions of Earth and Mars and their rates of motion. A hand crank allows the demonstrator to advance Earth and Mars while the gears ensure appropriate relative rates. Note that an arrow illustrates the direction of apparent motion in the sky, and we have placed background stars around the edge where we will see the apparent position of Mars. We start our demonstration several months before Mars reaches opposition. Remember that Earth is moving faster than Mars and will shortly overtake it. The rod connecting Earth to Mars points to Mars's apparent position in the sky. As we turn the crank slowly to advance time, Mars is initially moving eastwards. We have now reached the point where Mars's eastward motion appears to stop, the beginning of retrograde motion. Note that Mars is now moving westward. Mars reaches opposition at the middle of retrograde motion. We have now reached the point where Mars's westward motion appears to cease. the end of retrograde motion. As we continue to advance time, Mars resumes its normal eastward motion relative to the stars. Note that this effect is entirely due to perspective. Nothing changed in the motions of Mars or Earth. This diagram illustrates the perspective effect that underlies retrograde motion. At which lettered location in the sky does a superior planet appear to be located for the planet and Earth locations indicated? Please record your vote on a piece of paper and explain your method for determining your answer. To determine the apparent location by discussing the general superior planet.
Okay. So yeah, I hope that helped to explain a little bit about what retrograde is. So to sum it up, to answer the question that was posed earlier, so now that we've learned a bunch of fancy new terms, we can sum it up and to say that a triple conjunction is when the great conjunction of Saturn and Jupiter coincides with them going through retrograde motion, which enables us to see 3 conjunctions within a roughly 6-month period. So as I mentioned in the beginning of this talk, we sort of have this unfortunate thing that there's really cool, almost once in a lifetime occurrences happening. But the bad news is, as the conjunction gets closer and closer together, it's going to be harder and harder to observe because it sets earlier in the evening. All right, but I always like to end on the good news, which is you don't have to appreciate the conjunction when Saturn and Jupiter are at their absolute closest. In fact, I would argue, first of all, there's 2 things that are going to be really neat for the conjunction. Just go out every night, or I would say every night that it's clear, and just go and look at Saturn and Jupiter, and look each night to see that they're starting to get, just from your own eyes, closer and closer together. But for those that do have access to a telescope, I would argue what's really, really awesome and what provides the neatest opportunity with this conjunction is to be able to view Saturn and Jupiter at the same time through the telescope. And so in order to figure out how to do that, what I would say is start observing using a telescope when the scope's widest eyepiece will fit the 2 objects. So for example, if you have a telescope that enables you to have a 1-degree field of view, and I'll talk about in the next slide what that means. So if your telescope has a 1-degree field of view, you'll be able to fit Saturn and Jupiter in the view on around whatever this is, December 11th, 12th, something like that. Okay? And I would argue from this point onwards, Saturn and Jupiter will both be visible within the telescope. And I would suggest get out your telescopes and start observing around here. I'd say even go out a couple of days before then. But again, keep a note that before this date, Saturn and Jupiter will not be viewable at the same time through the telescope. So how you can arm yourselves with when this magical date will be. And so before we do that, though, as you notice, this magical date here is December 12th. And as you can notice, Saturn and Jupiter are now just barely visible within the field of view of the simulation. This is a simulation of what the view through the telescope would be on this date and time. Again, where Saturn and Jupiter are just barely in view, knowing that as each day progresses in the view of the telescope, they will be getting closer and closer together. So how do you calculate that? Again, in this example, I use this 1-degree field of view. Well, the way you calculate it is you have to know a little bit about your telescope. There's a couple of parameters that you need to find. First of all, there's probably a label somewhere on your telescope that will give you what's called the focal length of the telescope. In this case, 1200 millimeters. The next piece of information is you need to get the focal length of the eyepiece. Most eyepieces should have that stamped on it. In this case, this eyepiece is 25 millimeters. And then the last thing you need, which is the apparent field of view of the eyepiece. Some more expensive eyepieces will have that stamped on it, but if they don't, you can go onto the web and get the specs. In this case, the apparent field of view is 52 degrees. Now, you don't have to know what any of these terms mean. Just know that these are the 3 things that you need to know about your telescope. The telescope's the telescope's focal length, the eyepiece's focal length, and the eyepiece's apparent field of view. And you use this fairly simple formula up here to take those three parameters and combine them together to get the true field of view of your telescope. So in this case, the true field of view of this eyepiece with this telescope would be 1 degree, which is exactly what I used for this example up here. So with this telescope and this eyepiece, Saturn and Jupiter would be visible together starting on December 12th, and then get closer and closer as the days progress. So again, I'm just giving a couple of other little tidbits of information. This shows, again, the separation of Saturn and Jupiter as the days progress, the same figure that I've been showing over and over again. And this chart shows the altitude, or how high in the sky those objects will be at twilight. So again, there's this balancing game between making sure that Saturn and Jupiter are nice and high in the sky, because that's when they're most visible, but also closer together so that the visual effect is really neat. So conclusions here. First of all, the great conjunction of Jupiter and Saturn, I hope I've convinced you, is really cool. From two perspectives. One, just go look at it with no telescope, no binoculars, go out night after night and see how Jupiter and Saturn will be appearing to get closer and closer. But in my mind, the really, really great thing of this great conjunction is the really rare ability to observe both Jupiter and Saturn through the telescope at the same time. So I'd argue that's really cool. But more to the point, this is the last conjunction that will be visible from this side of the planet for another 40 years. And I'll allow everyone to do their age math to figure out the implications of that. However, it's going to be low in the sky near the horizon. So another advantage to enable you to make the most of this conjunction would be to find a location that has a really good western horizon. And by good, what I mean is as much as possible free of trees, free of buildings, free of other things that might block Saturn and Jupiter when they're low in that western sky. Next thing is try to find a telescope so that you would actually be able to resolve them and get a view of both Saturn and Jupiter at the same time. Now, with the Delaware Astronomical Society and Mount Cuba, during times that we're not in quarantine, we often take telescopes and go out into the public and share the views through telescope with the public. But unfortunately, because of the quarantine and observing good social distancing, we've not been doing that. So I would urge people, maybe dig out that telescope that you haven't used in 10 years and relearn how to use it, because this is a really great opportunity to take advantage and make use of that telescope. But the other thing is, observe it in the days leading up to the conjunction, as the Saturn and Jupiter will be setting later in the night sky. And the real key there is start observing with your telescope when that telescope's widest eyepiece will fit the two objects at the same time. So a lot of good stuff. Again, I would say start now. I've been kind of taking a peek at Saturn and Jupiter every night when I'm going out to do whatever. And it's really, really exciting. But for that, let's say that week around December, the week before December 21st, is when it's going to start to get really, really exciting.